Okay, so for question one, we watched the video and got a little bit of data. So the starting mass of the whole system was 73.3 grams, and that includes the the water, the copper, and the thermometer with the beaker. Our starting temperature was 23.5 degrees Celsius. And then after our reaction took place, we ended up with 72.7 grams as the entire system mass at the end. And then our final temperature was 58.1 degrees Celsius. So during this experiment, we saw both some physical and chemical changes. So this first one, dissolving copper in chloride water, we're going to say that this was a physical change. And that's because we observed that copper, that solid copper, that powder, and then we mixed it into some water and it made a homogeneous mixture. This means that we couldn't tell the two parts from one another and that there was no chemical changes taking place, so there wasn't any change in heat, there wasn't any change in temperature, there were no gases being given off, things like that. Number two here, or B, we had the aluminum foil being crumpled into a ball. We're going to say that was also a physical change. Sorry, I'm doing my best to write and not hold the paper at the same time. We're saying that this was a physical change for the same reason that we saw, similar reasons for why the first one was also a physical change. This time we just changed how it looked. We took a flat sheet of aluminum foil and we crumpled it up into a ball. We didn't exert any other kind of, pressures or chemicals or anything on it. All we did was change what it looked like. We made the shape different. We can flatten it back out. We can move it every which way. We can rip it in half, and it is still just aluminum foil. It's a bunch of aluminum molecules all connected together. On this third one here, combining the aluminum foil and the copper chloride solution that we made up here. And number one, this is going to be our chemical change. The reason that this is a chemical change is that we observed quite a bit of reactivity. The foil, when we first put it in, it started to dissolve into that solution that we had, the copper chloride solution. We started getting some bubbling. We got some sort of smoke vapor-like substance being, let off from the top of it. We had some color changes, and these are all classic indicators of a chemical change taking place. Bonds are being broken, different molecules are being exchanged between the aluminum foil and the copper chloride, and lots of stuff is happening here. Things are breaking down, other things are forming. No loss of energy, but we're just creating something new here. So we're gonna go on to number 3. So here it says, let's describe 3 pieces of evidence that support that a chemical reaction has taken place in this experiment here. So number 1, we're gonna say that the color change. So the color change, it was originally gosh, spelling that totally wrong. It was originally a blue color, like a cerulean kind of thing. And then we added aluminum foil, and we saw that color go from blue to a greenish, rusty red kind of color. Number 2, we are going to say this is a temperature change. A classic indicator of bonds being broken in chemistry, or especially covalent bonds, is a change in temperature, because it's a massive release of energy, right? So our temperature increased from 23.5 degrees Celsius to 58.1 degrees Celsius. So we had a change of 34.6 degrees Celsius here. So that is another indicator of this chemical change. Number 3, which we've already discussed a little bit before, was that we produced a gas. So the evidence of this gas was sort of that steam-looking stuff that was sort of coming up off the top of that beaker. We also had some condensation going on the sides of the container. And really what we saw was a loss of mass, which could be explained by this gas. And that also tells us that we have a chemical change. So number 4, we just said this a little bit. So the mass of the system decreased from the start to the end. So here we're asking, does this violate the law of conservation of mass? And we are going to say no, it does not. This is actually a very good example of the conservation of mass, conservation of energy. So sort of to explain how this is going, the mass was changed because something within this reaction was used as a fuel, right? We lost energy in the form, we lost energy from the beginning, because it was sort of used as a fuel, for lack of a better term. So the energy that was released as a result of these bonds breaking was that heat, and then from a product of that heat was the steam, right? So we can feel the heat, and then we can see that the steam is condensing on the edges of the container, but we don't have anything telling us over the top, right? So the steam has physical mass, and it is evaporating. It's getting out of that container. It's going out into the world, right? So the mass is still there. It's just changed what it looks like a little bit. It's not in that container anymore. It's been heated up. It's changed states, and it's now in the air, but that doesn't mean that we've lost anything. We now have a mixture that incorporates the copper chloride solution, and then we also have the aluminum foil, which are all in there, right? But we have a smaller amount of that aluminum foil, or what we can physically see as a smaller amount. It looks like a bunch of these broken up pieces within this beaker, right? We've got that solution there. So we're making a heterogeneous mixture because we can see pieces of the aluminum foil, we can see deposits of the copper. But just because it doesn't look the same doesn't mean we lost anything, right? If we were to try to measure this, I think might be a good way to explain it. We tried to measure this in a closed system, and that closed system was on a scale. There was no way for the gas or for that water vapor to escape a closed box, but this reaction is taking place in a beaker inside that box. The weight of that box, of everything that's within that box, is still going to come out to our starting 73.3 grams. This final mass, we have that loss of 0.6 because things have evaporated, they've left that container. So now that they're out in the air, we can't weigh them. They're not still in the same place. Hope that makes some sense. So for number 5 here, we're going to move on and classify each of the following as an element, compound, homogeneous mixture, or a heterogeneous mixture. And again, I think we've already done a little bit of this. So here for copper chloride powder, here we go. We're going to go with a compound for this, right? And that's because we have the copper and we have the chloride, right? So we're adding these two together. These would be elements. These are each element. We add them together, it becomes a compound. So that's why we're going to go with that. And the second one, copper chloride solution. So we're mixing it in water. We're going to call it a homogeneous mixture. That's because this copper chloride has dissolved into this water. It's created a solution, and a solution is interchangeable with a homogeneous mixture. The way that we know for sure that this is a homogeneous mixture is that we cannot see, once it's fully mixed in, right, once the solution has been fully mixed together, we cannot differentiate the water from the copper chloride. They're evenly mixed throughout all of the solution, so we can't actually determine which part of that solution is the copper chloride, and which part is the water. They're indistinguishable at this point. So aluminum foil, we're going to go with this element, and that is because all we have is a bunch of aluminum atoms, and they're all just connected to each other, and that gives us a sheet of aluminum foil. When we crumple it up, remember we changed the physical component, or the physical expression of it, but we didn't change anything chemically. So we just have a bunch of one single element. Actually, would we call this a compound because they're all connected? No, we're going to stay with element because they're not different. We don't have two different atoms, we have a single type of atom, and they are all put together. So we're going to stick with that. So copper chloride solution aluminum foil ball, we're going to call this a heterogeneous mixture. We're going to go with that because, you know, at the end of this experiment, you could see pieces of copper and aluminum, or at least that's what we can assume that's what those are. Those are the two metals that we've added here, and then we see deposits within that solution later. So because we can distinguish one part of that mixture from the other, we're going with heterogeneous. We can see little globules or whatever floating in that water, so we can distinguish between the different parts of it. So for number 6 here, the question is classify each of the following elements as a metal, non-metal, or metalloid. And for copper, we're going to say this is a metal. And that's because metals are solid at room temperature. They have a shiny appearance, they're conductive, they're malleable. And copper is one of these things. It's shiny, we use it in electrical work, so it conducts quite a bit of electrical stimulus, and it can be twisted, bent, cut, and re-put back together in all sorts of ways. And that is what a metal does. And based on those same properties, we're also going to say that aluminum is a metal. A non-metal, so the opposite of what we have here, is chlorine, and we're going to have chlorine as a non-metal because it's brittle, it's solid, it does not conduct electricity, it is not malleable in its purest form. It's crumbly, brittle, and just doesn't do what a metal should do, which means it's probably not a metal. So I'll make a little note here. So we've got shiny, conductive, malleable. And we've also got that here. And then for our chlorine, we have non-conductive, not okay, so there we go for that one. So for number 7, ooh, this sounds good. Okay, just a moment. Let me get my notes here. So, for aluminum, 28, right? So, in this expression here, 28 equals our atomic mass number, right? And to be able to figure out how many of each type of, subatomic particles we have within this atom, we have to solve this equation, which is atomic mass equals number of protons plus the number of neutrons. So when we're looking at aluminum 28, if we refer to the periodic table, which I don't have right in front of me, we will see that the number of protons that we have, which is equal to the atomic number on the periodic table, we have for aluminum is 13. And because we know that the atomic mass here is 28 because of how it's written, we had 28 here. And we're going to put neutrons as n, right? And now we're going to solve for n. So to do that, all we have to do is subtract 13 from each side of this equation, which brings us to 15 equals n. So 15 neutrons. All right, so when we put this all together, we have a mass of 28, which equals 13 protons plus, actually, that's not a good way to write it. 28 equals 13 protons, 15 neutrons. So the other part of this that we're missing is solving for the number of electrons. But what we've also learned in this class so far is that the number of protons in an atom is equal to the number of electrons. So protons equal to number of electrons. So at the end here, we'll just state it a little more clearly. We have protons, 13 of those, neutrons, 15 of those, and electrons, 13 of those. So we have 13, 15, 13. And those are the answers that we're gonna go with here for number 7. All right, and here, number 8, I did find this one just slightly difficult. We're gonna start with aluminum and chlorine, right? So aluminum, we know, has 13 electrons. And we can look at the periodic table and find that chlorine has 17 electrons. It has 17 protons, which means it has 17 electrons. Same with pure aluminum. And copper, we have 29 electrons. So in order to figure out what this oxidation number is here in this type of atom, or this type of molecule here, we, what am I trying to say? We are either adding or losing electrons to gain neutrality within the atom. And neutrality, and by neutrality I mean that it is stable, that it's the most stable. So for here, aluminum, most stable means that the outer, shell of electrons, we have, right, the nucleus, we'll denote that with N, and then we have the first shell, second shell, and third shell. So each of these shells can hold a certain number of electrons. The first one has 2, we'll put that there. The next one has 8, 1, 2, 3, 4, 5, 6, 7, 8. So we have 10 total of electrons right there right now. So aluminum has 13, right? So we're adding 3 more in. But this is an ion, right? We have a charge here because there's either 3 electrons more than stable or 5 less than stable. So we want a full shell on the outside, and that's what we call the valence shell. It's the outside shell of electrons. So here we have 13 there, which means we need to lose 3 electrons so that we have a full shelf, right? So it wants to gain or lose as little as possible. 3 is smaller than 5, so we're going to lose 3 rather than adding 5. When we lose 3, we end up with a positive charge, remember, because the electrons carry a negative charge. Okay, so here for this one, we're going to say that our oxidation number is equal to its to the number of ion. So it's, I'm sorry, the ionic number that we have, and that's going to be plus 3. That's what we're going to stick with because we have to lose 3 electrons, which means we're gaining a positive charge here. Same thing down here for chlorine. We'll say our nucleus is here. We have our first ring with 2. We have our second ring, 2, 3, 4, 5, 6, 7, 8. Second ring with 8. So that's 10, and our next one, so we have 7. 1, 2, 3, 4, 5, 6, 7. All right, so we have 7 here. So for this to be stable, we want to add 1 electron to that outer shell, to that valence shell to make it full. So because we're adding an electron, we're adding a negative charge, right? So our oxidation number is going to be -1 for this one. Oh wait, hold on, no, I got that wrong. One of these is wrong. Hold on. Oh no, I think that's correct. That's what we're going. That's what we've got. We have to add an. Yeah, we're adding an electron, so we're getting negative charge. Never mind. I'm all good. So copper here is the one I actually struggled with. I think we're going under the idea that the third valence shell has 18 electrons, but from what I thought I knew, I thought we only had 8 in that third valence shell, which is making me really a little bit confused. So if we do it that way, then we start with our nucleus. We have 3, and then we have a 4th valence shell, right? But we're sticking with 3, and we're gonna end up with 18 here. So because we have 29, we have 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we still need 11. You know, I've been looking at this one for so long and I cannot figure it out. I feel like the answer either has to be -7 so I thought it either had to be -7 or -1. So it's -7 if this shell, so I'm sorry, if the 4th valence shell has 18, I believe the number that we would get is -7. But if we're in the third one and that is the one that has 18, then we're only -1. Well, thank you. Have a good one.